Woohoo! Welcome back. Today we're going to be talking about volumes. Yay! And we're going to be building up on what we talked about in the previous section when we were talking about the area between two curves. And believe it or not, it seems impossible to imagine how the area between two curves, which is 2D, could possibly be related to volumes, which are 3D. But we're going to do it anyway. It's just magical. So make sure you have something to drink, something to hydrate, and maybe even a little snack. This section is really long, so I'm going to have to chop it up into lots of little videos so that, I don't put anyone completely to sleep. But Lowly Worm is here to remind you that no matter how twisty it gets, it's still going to be okay. So let's go ahead and get started. Woohoo! Yay! So where we're going to start today is just a little bit of practice. Today's video is going to be all about how to use integration to find the volume of an object, which is kind of weird because so far integration is just about the area under the curve. But let's take a look at a really cool object. And this is called a right cylinder. No, there are no wrong cylinders. All cylinders are just fine. But a right cylinder specifically means that it is standing straight up. It isn't, like it isn't a cylinder that's kind of like tipping over to one side or something. So we've got a cylinder, and basically a cylinder is a circle on top, a circle on the bottom, and then a piece that goes all the way around. And believe it or not, this piece that goes all the way around is a rectangle, which is kind of cool. And if you're not sure about that, if you have a can of something like a can of beans or a can of corn or whatever you have canned, I guess you don't put monkeys in a can, you put monkeys in a barrel. So I can't think of what else would go in a can. But if you've got one, and if you take the label off of the can and unwrap it, you'll get a rectangle. So that's kind of cool. But the other thing that's cool about cylinders, and this is what I want you to start thinking about as you go out in the world and you see all these objects in 3D world, assuming none of you are secretly like cartoons or sim creatures, like Lowly Worm, who looks 2D but is technically 3D actually. There's a little bit of width right there, just a tiny bit. So everybody's got a little bit of depth, even when it doesn't seem like it. So for these objects, a cylinder is nice. You want to start thinking about how do you make this object. And one way to make it is, like I said, circle on top, circle on the bottom, and a rectangle around. But there's another way to make it. Pardon me, Lowly. The other way to make it is to take a circle and then put another circle on top. Put another circle on top. Now, my circle drawing abilities, this probably is going to start to remind you if you've ever been to a fair where they have you take the circles and you try to completely cover the spot, and it's really difficult. It's going to look like I'm playing that, but that's not my intention. My intention is to try to draw a cylinder, but I fear I have failed already. So hopefully you can imagine the platonic ideal here. And what we're trying to do, pardon me, I'm going to move Lowly over here. Part of what we're trying to do is we're going to stack circles in a vertical stack, a right cylindrical stack. And in doing so, I can create this cylinder. So I want to try to convince you that a cylinder can be seen as a stack of a bunch of circles. What do you think about that? And so the volume equals adding up all the circles. And so what would that mean? Well, the circles are pi r squared, right? If I've got a circle, and I know what the radius is, and we can see, oh, I covered it up, so it's hard to see now. Sorry about that. But it says R. R is the radius here. So here, the area is going to be pi r squared, right? That's the area of a circle. And if I stack a bunch of them, how many do I have? Well, now this, I'm going to wave my hands magically and say, don't worry about how many circles there are, or the fact that I'm using the word circle, which is 2D, and then trying to make a 3D object, because it's not, doodle-doodle-doo. Don't worry about that part. Believe me when I say, maybe believe me, that you can take pi r squared, and instead of multiplying by how many circles there are, which there are a lot, you can simply multiply by the height. And we can see it as a stack of that many circles. What do you think? I can already see some of you are like, So what I'm going to say is this volume is true. The way I'm describing it, yeah, it's not exactly, it's a good way to look at it. It's more metaphorical than anything else. But you can see it as a bunch of circles stacked up. And in fact, once we use calculus, we are going to see that, yeah, it is a bunch of circles stacked up. But it doesn't quite work the way I'm suggesting, where you just multiply by h. But let me show you. So what is the volume of a right cylinder? It is exactly that. It's pi r squared times h. This is the area of the base circle / the top circle times the height. That is exactly right. So I wasn't lying about that. Thank goodness, right? But how do we get there? And that's a really good question. So this is where we're going to start practicing using calculus for something unexpected, perhaps. Now, Lolly Worm's gonna step out. I don't want him to get squished. Okay, you guys ready? I have written a description here, which honestly, even I have trouble reading. This is quite a statement. Draw a picture of a cylinder lying sideways. Okay, sideways looks like this, right? Oh, that's beautiful. Gorgeous. With its center height aligned with the x-axis. Okay, what is the center height? Well, that was, let me go back up here. That's this, that point in the center of each of these stacked up circles, that center that sits together and it makes a height. We want that to run along the x-axis. And I know, at the first time I did this, I was like, what even in the what are we doing here? And the answer is, we're gonna switch off pens because this one is not so happy. Let's try a different one. Let's see how this one goes. Okay, you guys ready? We can totally do this. So I'm gonna draw my cylinder. And I mean, I'm putting effort into it. You can't tell, but boy, this is heavy concentration here. And we've got all these circles, right? Got all these circles stacked up. And then over here, I am going to draw the central height that comes out of the middle. That's the x-axis. And then I'm going to draw right against the base. This is the y-axis. So the can is sitting up against, and I'm looking to see if I have anything I can grab. And I can kind of grab my water. Oh, thank goodness someone left this sitting on the table. Seriously, I didn't even plan this at all. I've got a cylinder. I want to put the cylinder up against the y-axis like this, like that. So the y-axis is sitting right along the base like that. And I want the x-axis to come right through the center. So that's what I'm trying to do with this. This is our little cylinder like that. Oh, thank you, mysterious person who left a soda on the table. Yay. So I want that to look like this. And then the next question is, what values can I identify on this? Now you notice that I'm trying very hard to use a set of 2 axes and not 3. So in fact, I've just got the x-axis and the y-axis, and we're not saying anything about the z-axis because we're not going to really deal with that until the next section, your next calculus class. We kind of force things into 2D. But what are we going to do with the values? So in other words, think about what values there are. Now, if we go back over here, I, of course, obliterated it with my lovely sketch. But a cylinder basically has only 2 dimensions to it that we consider in terms of values. Now, the radius goes off in many directions. That's why it's a 3D object. So we've got a radius, and that talks about how big the circle is, right? And then we've got the height, which is how tall the stack is. So in terms of R and H, what have we got? Can I convince you that right here on the edge, right there on the top edge of the can, this little dot, I claim, is at the coordinates of H and 0. It's right in the middle, so it's not above or below. It's right on the x-axis, so y is 0. And this is the height. What do you guys think so far? Okay. Now we got to figure out what R is. R is going to be the radius. So there's a point right here where it's on the y-axis and it's gone up half of the circle, right? Not the full diameter, but R. So that's going to be the point at 0, R. And because of that, this is the point at 0, the opposite of R. What do you guys think? And I mean, it can get even more exciting. We can point out that this point is going to be at the point H, the opposite of R, or negative R. And this point right here is H, positive R, right? So we can really go to town. I can say if this is exactly halfway, then this is going to be 1/2 HR, 1/2 H, negative R. And we can go to town. We can come up with a lot of different values on our graph. But that's going to give us a good start. The next question I'm going to ask, which I already asked up there, so it's going to be an easy peasy answer, I hope. If you take this can and you go slice, what are the cross sections? Well, there's a hint right there. There's a hint right here. What are the cross sections? There's another cross section right here. Uh-oh, I'm taking us to Smeary Town. Sorry about that. Won't you take me to... Oh, no, I promise not to sing anymore. So, never mind. What was I saying? I don't know. So, what are the cross sections of the cylinder? The cross sections of the cylinder are circles. And again, the circles have radius R. Oh, I drew it before I... Let's see if I can be creative about not running over myself. Try not to take us to Smeary Town too much. Okay, there we go. Not too much Smeary Town. But the radius is R, right? So we've got a bunch of circles. And so what am I going to do with these circles? So let me see if I can kind of get this page plus the next page, kinda, sorta. I'm trying to break a few laws of physics here. It's okay, it's not a physics class. We're totally allowed to do that in math. Physics, you can't. And of course, you never break the laws of math, because why would you break the laws of math? They're the best laws there are. Okay, use the techniques from 110A to express the volume of the cylinder as a definite integral. So let's think about this. Now, I've got a hint here that kind of gives the whole thing away. Add up a bunch of circles. So, what am I going to do? What is a definite integral? Remember, a definite integral is that S guy. And it was S for sum. I believe it was something else in Latin, but the good news is Latin and English share a lot of letters, so we still got S. I can't think of what it was in Latin, though. We got the circle here, circle, 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 circle. And I want to go from the y-axis. So we're from x equals 0 all the way over here. And what does x equal here? X equals h. So what do you think? What would you think? Ooh, don't look there. What would you think if I... Oh. Don't give it away. Shh, no spoilers. What would you think if I took a definite integral? Remember the S guy, the summation. And remember I put the bottom of the can right at the y-axis. And the top of the can is when x equals h. And I took the area of a circle. And I multiplied. Now, remind me, when we add up a bunch of things, what's the width? Oh my goodness, I'm gonna regret this. Trying to draw this. What is the width? The width of each circle. So remember back when we were doing our rectangles and we had the height. In this case, instead of a height, we have a full circle. But it's basically the same thing. It's just a rectangle that extends above and below, which we've already done in the first section. But with the width of each circle could be delta x, which then in the integral becomes the differential dx. So this is the area of each circle times the little width. And this is what I was fudging earlier. Because if you add a bunch of circles together, you don't get anything because they're 2D. You don't stack them. They don't have any width. So what we're going to do is we're going to give them that little dx width so that we can actually create a 3D object. So here's the area. And there's the little width. And so we're going to get these little slices of a can. Now, what was the area of the circle? We're going from 0 to h because we're counting in x. The area of the circle was pi r squared dx. What do you guys think? Kind of cool. And now you can start imagining, well, we could do this with a lot of things. It doesn't have to be a can. It could be a box. It could be anything three-dimensional if we know how to calculate these little slices. If we know how to get the area of each slice, we can add a bunch of them together. So let's go ahead and figure this out. Okay. So I have something written here. The book really loves it. So let's talk about it. It's always important when the book really loves something, you got to look at that. So it's got a of x, that is the area of each circle. And then all of a sudden, a pops out completely outside of the integral, which is very exciting. Why can it just pop outside? And notice that this over here says a of x, and this just says a. Now, up till now in math, my guess is that a lot of the time when you read math, you were like, la, la, la. Okay, that's weird. I'm ignoring it. Let's move on. It's probably not important. At this stage in calculus, every little teeny tiny change is really important. And so I really encourage you, I want to challenge you. When you see something suddenly change like this, you need to be able to explain it. And if you can't, come to me. I need to be able to explain it. I should be able to say, oh, that is this, or that was a typo, or good eye. I have no idea. Let's go figure it out. So in this case, I'm saying the area of each circle as a function of x. Notice that area is not a function of x anymore. It's just It looks like a constant. So tell me about those circles. The circles, the area of the circles, there's no x. It doesn't depend not of, on. Oh, prepositions, they're hard. On x. So if it doesn't depend on x, we can pull it out in front and not worry about it. So what does that mean? Okay, the volume, 0 to h pi r squared dx. Now there's a rule when you're calculating definite integrals. If this is a constant, if this has no x's in it whatsoever, you can just pull it out of the integral. And now at this point, we're going to have to remember how to integrate. Remember backwards derivatives. So dx rises up one level. We're going to give it a promotion of one level of x. And that's going to be, it's basically 1 dx. So it becomes x between 0 and h. So that's pi r squared times, remember you plug in x equals h minus x equals 0. So that's going to be pi r squared times h, which is our volume. Yay! And that's what I told you it was before, but now we've shown it using calculus, whatever we're doing right now. Woo, calculus. Okay, Lily Worm, it's safe for you to come back. You will not get squished by the can. Okay. How you doing, Lily Worm? Was that all good? Woohoo, yay. Okay, so I bet you're asking, okay, that's fine, but what about something that maybe is more like Lily Worm and goes, wow, 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 and it changes size? And the answer is, yay, let's do that next. So in the next video, let's talk about what happens if it's not just a can that stays the same. What if it's something goes wah, 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 like that? No, not like an alligator, but maybe something like a sphere. How about we start with spheres? Alligators are very advanced. Plus, they don't stand still. You try to put them right at the origin, and then they move around unless they're very sleepy. So, so that's it. That's what we're going to do next. So, it's been almost 25 minutes though. So if you've watched this straight through, please go look at something green, look at the sky, go outside, get some air. If it's raining or snowing or sleeting, you could still go outside, but maybe you want to, bundle up first. You definitely go get a snack, get some hydration. Remind yourself that you're awesome and amazing, and you are studying a subject that most people never get to in their lives. So congratulations, you're awesome and amazing. Lily Worm thinks you're awesome and amazing. And, when you're all done, come on back here. Let's get together and let's study spheres. Woohoo. Math on, guys, math on.